Now the title of my talk is The Beauty and the Beast. And it's really going to talk about my journey toward developing sustainable rose cultivars. You know, those are easy to take care of and things like that. And let me see if I can get this right. Okay. And so, of course, the beauty is a rose, but the beast are the diseases. And we have some wonderful ones that we work with. Rose rosette disease, hopefully none of you have seen that, but I fear that probably some of you have. And of course, black spot, I'm sure all of you have seen a little black spot here and there. It's just everywhere, and I've seen it everywhere I've gone, whether it's China or South America or Africa. I've seen it everywhere. It's just amazing. No matter where I look, it's there. And so that's sort of where that is. Now, whoops, I went too far. Let me see, go back up. Okay, so my journey started with peaches, actually. I'm not a rose guy, believe it or not. When I was in graduate school, I wanted to work in vegetables or fruit. And so my first job here was working on peach breeding, which I actually still do. And I was also, actually when I was a graduate student, I interviewed at Ball, and they said, why don't you go to Costa Rica and interview there, because we have an ornamental breeding position down there. And I said, I'm not interested. See what happens? You never know what's going to happen as you go through your career, but it's lots of fun. Just go with the punches and have lots of fun with it. But yeah, I've bred peaches for the last 40 years and developed about 30 varieties, about 10 more to go, with all sorts of types. There's whites, there's yellows, there's no city, low acid, you have the flats, you have the nectarines. I got all types of things adapted to Texas, from up the Dallas area all the way down the Rio Grande Valley. So a lot of interesting stuff that's been released. But we're not going to talk about that. That's where I started. But then in the early 90s, I met this fellow, Dr. Basie. He's a retired mathematician out of Texas A&M. And he taught things like imaginary numbers and things like that, which I have no clue what they're about. I've heard about them, but that's it. But he could explain it. But I never asked him to. We talked roses. And so his passion was rose breeding. And he did it as a hobby, but he's a real serious hobby. He wanted to get roses that were adaptable to this area. His main focus was black spot, because that was before rose rosette was really raised its really ugly head. It sort of had a little ugly head elsewhere, but not here in Texas yet. And so I used to go every Friday afternoon and visit with him, and in the afternoon we'd have chocolate ice cream and coffee, and then look at roses, which is typically normal, right? But he was really focused on carefree roses, and he focused on chromosome numbers. And you see in roses we have diploids, which have 2 sets of chromosomes. That's what we have. We have 2 sets of chromosomes, but plants are weird. They can have 4 sets, so they can double that, and that makes the genetics a little more complicated. Now I'll talk a little about that a little later. But most of our commercial roses are tetraploid, which means they're, from a breeding point of view, they're sort of complex and interesting and challenging, and kind of, well, for me, just lots of fun. But his emphasis was disease resistance, and of course he released things like Belinda's Dream is one of his, and Basie's Blueberry, Basie's Purple, various things like that. So he's had a little things. When he said he released it, what he means, he gave budwood to a nurseryman and said, go propagate. That's how he released. And it worked well for him. Okay, so Dr. Basie got me started on roses, and he actually endowed a chair before I met this fellow, Ralph Moore. And his chair, he contributed or donated $500,000 to university to start a chair in rose genetics, which I hold. And that bought, and this was in the 90s, so for 30 years, it made the university do rose research, because before they weren't doing it. And in the span of those years, I brought in about $15 million of funding. So really, it's a pretty good return on his investment. So he got a lot out of that $500,000. But later, I met Ralph Moore, who, if you don't know, is the father of miniature rose. And he bred about at the same time period as Dr. Basie, and they knew each other, but they never met each other. And Ralph Moore used some of Basie's materials later on his breeding career. But he released about 500 different varieties. 300 were miniatures, and then 200 were all sorts of other things. And his focus, he was in Central Valley of California, so not a lot of disease pressure. A little powdery mildew, a little black spot, but not too much. So he focused on unique horticultural traits. Things like, of course, miniatures, moss roses, halo roses, stripes, all sorts of interesting things. So he did a lot of work there. But he also was real concerned about sustainable roses. So both these gentlemen were thinking of sustainable roses, and that's sort of where I went in my breeding and in the program. And so a sustainable rose for me is something that's basically well adapted. Okay, so it's got to be disease resistant. It's got to be here in Texas, able to take the heat as well as cold, drought tolerant. Of course, beyond that, of course, it's going to be easy to maintain. It's got to be easy to propagate if you want anyone to use it. So from a commercial point of view, but it's got to be productive and beautiful. If you do a study, or they have done studies to look at the willingness to pay for roses, the value of adaptability is much higher than that for ornamental traits. So a beautiful rose, if it's adaptable, it's worth more. And so that's where a lot of the breeders, and Mike was right, a lot of breeders over the last 20 years have been looking at better adapted roses, not just the gorgeous ones. So you get a lot more shrub roses that incorporate other species and stuff into the China-European base for roses. And so that's where a sustainable rose is. And of course, a couple larger trends that sort of feed into this is the trend for convenience. I mean, who wants to spend a lot of time gardening, right? You want to plant something, you want it to grow. If it doesn't grow, I always let it die and plant something else myself. And that's what most people want to do. I mean, there's others that want to spend a lot of time and effort to produce them, and that's fine. But also environmental stewardship. Again, don't want to contaminate the environment with all sorts of chemicals and what have you. And that's good too. So that sort of all goes towards better adapted, disease-resistant roses and plants in general. So adaptation traits, again, very important. And if you looked at the US, and I've done surveys to figure out, and of course just talking to extension people and what have you, the two most devastating diseases in the US on roses is rosette disease and black spot. Now, there are other diseases, no doubt. In certain areas of the country, they're very devastating. But in general, those are the two major ones. So that's where we focused in our research. And so basically consumers want a beautiful garden that takes care of itself. Who wouldn't? You want to plant something and let it go. I don't want to spray, I don't want to prune, though I do prune a little. And so the breeding program at Texas A&M is always focused on well-adapted garden roses. Okay, so disease-resistant, heat-tolerant, high number of flowers because, you need a lot of flowers for a good rose. And of course, you have to look at horticultural traits. So you got to put the whole package together. Now, we focus on the more adaptation side of it. And for remember this endowment was started in early 90s, and it was really hard to find funding. So we sort of did a little work on the endowment money, which was about $25,000 a year that it produced. And so we did that until 2009. We got a little funding through a specialty crop research initiative grant, which was the first granting program in the USDA, the federal level, that focused on specialty crops that included ornamentals and not just edible crops. Because we'd always be beaten out by, oh, you can't eat that, so private people should do that. We don't want to give you funding for that. Well, this changed the game. And so the first time I managed to slip in on a grant was one that included the whole rose family. So it didn't just include roses, it's peaches, because peaches is part of the rose family, as is rose, but also apples and pears and almonds and plums and cherries. They're all rose family stuff, which is good, because that means we can get money to do some rose work, which we did. And so we started doing rose work on disease resistance in this particular thing in 2009, so we actually had some funding to start ramping up the work. And you notice one of the objectives here is marker-assisted selection. And now most of you are sort of glazed over now. This is appropriate. So what is it? And why use it? Now, myself being a breeder and of course a professor and sort of a science geek, this is normal for me. And to really explain it, I sort of have to explain the rose breeding cycle real quickly. I won't take a lot of time at this. But if you're doing rose breeding, the first thing you do is select your parents, right? Because what you're trying to do is select the families that give the children that are the best. It's not like our own children that we can throw away and keep. No, we can do that in roses. We can't do that for ours. We got to keep them all, right? But here, I can select a female and a male or a pollen parent and do the cross. So it's hand pollinations. And we do this in the greenhouse. We do thousands and thousands and thousands. We, the royal we, help with my graduate students and technicians, and I do a few, but mainly is I tell them which ones to cross. And so we remove the anthers, you can see that there, and then we take the pollen from the anthers and put it in a little tube and then take a makeup brush, actually. It's always fun going to the store and buying a dozen makeup brushes. They sort of look at me and say, what the hell are you doing? So, pollinating roses, isn't that obvious? And so anyway, so I take this and I take the pollen out of the tube and put it on the stigma of the female to make a specific combination, right? I want a specific family to create, and then you pollinate the flower and it sets. And now when it develops, it's the hip under the flower that develops, and that's where the seed are developing. And so that takes basically all season. They aren't ripe till September or so you got to be patient. You're doing the pollinations in, March, April, May, and then you have to wait 3-4 months. You go ahead, and then you get out the seed, and this is actually a little box of seed from Rosa brachyata. Now, I would not advise you to plant brachyata all through the yard because it does grow well. And I mean, it has nice white flowers, but only once a year and lots of thorns. So anyways, but that's what they look like. And then we plant them out in the greenhouse. And then we take these and we put them in, okay, there's more seed planting. And you can see we're planting about 1 inch by 1 inch because our germination on roses is not 100%, not like peaches. Peaches are easy. Roses, you get, if you're really good, you get about 40% on average. But if you do the weird crosses I do, well, you can expect about 5 or 10%. So, but that's you just do a lot more crosses. And then you put them in the cold room because they need a little cold stratification to germinate well. And so we plant them and then put the whole watered flat in the cold room so we don't have to mess with them anymore. And then we take them out in January, put them out in the greenhouse, and they start growing. And you can see they're starting to grow. This is the second year. So the first year we did the cross, the seed developed, we harvested them, we stratified them. Second year they start germinating. So this is your second year. You're in the greenhouse, and you can see they're starting to germinate and get flats and flats of these thousands of seedlings you have to go through. And you can start selecting. You know, we get wonderful powdery mildew. And you might say, wonderful? Well, for me, it is because I want to see something. If it's susceptible, I want to know it. And then I can rip it out and throw it away and say, it was a bad parent, a bad kid anyways. They don't need them. Anyway, so I go through that. But also within 6 weeks or 6 to 8 weeks, they start flowering. So you can begin to select for flower type and flower color. Not necessarily the size of the flower, because a lot of times on a small plant, it's not going to be maximal size, but you can do a lot of selection at this stage. And so hopefully at this stage, you can eliminate about 50% of your seedlings. So you start out with 10,000, you end up with 5,000. And that's great. Okay? And so you take those, you put them in little bigger pots, and then here in the fall time, we can put them out in the field. And so we put them out in the field and then see if we can kill them out there. It's all about eliminating, right? And so if they get too much black spot, they're out. they don't look nice as a bush, they're out. You know, we make up excuses to eliminate. And we have an idea of what we want too. You know, there's both things going on here. And so they go out in the field, and then, so the first 2 years you're doing the crosses in the greenhouse, you're growing seedlings in the greenhouse. The second 2 years you're in the field under adaptation trials to see if they can grow in your environment. And so you want to encourage disease, and sometimes I've had overhead sprinklers trying to wet them down to make sure that black spot spreads well. You know, anything to make more disease and have fun. And so you go through and select, and of course there's some very obvious things you eliminate. It's easy to eliminate at least another 50% just because they lose their leaves too quick. So you want something that maintains leaves. Now you'd like some good flowers too, and you can see in this picture that the one that has the most leaves doesn't have any flowers, a little detail. But at least it has leaves, you know, so that's a good point. And then you look at things, and there's all sorts of flower types, there's all sorts of growth types, and there's lots of possibilities in roses. You need all types of flower types, all types of growth types, depending on what you want in the garden. So you could go wild in your selection and over-select, but so you have to have some focus. And so that's year 3 and 4, okay? And so your seedling selection, you can see there's a wide range of different flowers you can get beyond the flower type or the plant types, a lot of flower types too. You gotta go through and pick out the ones you think are best. With respect to the flower duration, we look at how intense the flowering is and how often it comes on, the size of the flower, the number of petals, the color, how well those petals fall. Because you really don't want something that has great petalage and then just turns brown and just gets ugly. You know, that's not always what you want. So there's a lot of things you got to look for. And so in summary, this is sort of the breeding cycle. It's at least 4 years, but it could be more than that. And that's 4 years from cross to cross. So it takes me 4 years to figure out which ones are the best parents for the next generation. Okay, so I have 2 years in the greenhouse, one for making crosses, the other growing the seedlings, and then 2 years in the field. So it's a 4-year cycle. Okay, so if you're breeding and you want to release something, so after you've gone through all these selections and you start out with 10,000, you eliminate half of those, 5,000 in the field. You eliminate hopefully all but maybe 50 of those. So you're really throwing a lot away this field step. You come out with your advanced selections, so 50 every year, let's say. And so another 3 years to figure out, you know, which will be the one to release. So from 50, you hopefully go to 1 or 2, but no more. So out of 10,000, you whittle it down to about 2. And so it's quite a process. And so if you're breeding commercial roses, it's more likely than not you'll go through 2 breeding cycles and then 1 evaluation cycle at least. And so a minimum of 11 years. So to release a variety from cross to release about 11 years. It may take longer, but that's sort of the minimum. So it takes a long time. And I only have so many years in my life, so I'd like to make it quicker. You know, to have to wait 10 years, that's a long time. So marker-assisted breeding is all about making it quicker. And so what we do here is, let me see, basically what we would do, so this would be marker-assisted selection breeding. So what we can do here is that if we have the DNA sequences, so we take the DNA of every variety, or every seedling that we want, and we go ahead and characterize it so we know the sequence there. And then we associate that sequence with specific traits. Okay? If we do that, we can use the marker or that DNA sequence to tell me whether it has a trait or not without seeing the trait. So I can do a seedling, do the DNA, and eliminate it before I can see a flower or how well it's adapted or anything. So instead of putting 5,000 out in the field, I can probably whittle this down to the best 50 or 500 very easily. And so a lot less field work. I can spend more time on those and then do better characterization of the best ones. And I don't have to worry about all the garbage. because I can eliminate most of that early on. And so that's the whole idea here. So you can do a much quicker evaluation and cycling of these things. So in this scheme of things, so if I have 11 years, if I can do a 2-year cycle, I can do 4 cycles instead of 2 cycles, which means I can do twice as much. Okay? So, and hopefully I can get everything in there. And when we talk later about my work on stacking disease resistance genes, you'll see why I want to do this. So the whole key here is using the DNA sequence to mark a specific trait, so you can follow it with the DNA sequence and you don't have to look at it for the trait. So you don't have to spend 4 years, you can do it in 2. And so you're decreasing your breeding cycle by 50%, decreasing the number of seedlings you put out in the field quite a bit too, so there's less work in the field. And so, you know, from a breeder point of view, you say, well, I'll start more in the greenhouse so I can use all my field work, right? Well, you could do that too. And you can improve your parental selection because you're doing better at selecting parents because it's not just what they look like, but you know the genetics behind them. You know what state everything is. And so you can select your parents even better. And so that saves you a lot of time too. So you're starting with better stuff to make better progeny. And then once you get the families out there, you can eliminate the trash a lot quicker. And so it's a way to make things quicker. And so that's where a lot of these projects were going, was to how do you breed quicker and better? And so, marker selection, we do need plentiful molecular markers. So our DNA sequencing equipment and technology is improved tremendously. So we're way ahead there. But we also need computational tools. And I'll talk about that a little later with another thing. Because again, diploids are easy, tetraploids are a little more complex, and not many people work on those. And so we needed to do something there as well. Now, in 2009, that's when this rose breed project ended, and I tried to get rose project going, and I put 2 or 3 in, and of course they didn't fund it in this time period. But the American Rose Society Research Trust Fund helped us get some preliminary work done so we could continue applying for funding. And so that was very useful. And then a really important thing happened. Now, remember, up to this, I've only talked about black spot, really. And in reality, rose rosette was not on my, my radar at all until 2013. The industry came together and said, hey, why don't we have this rose rosette conference? We'll all get together because it was starting to cause a lot of problems and more north of us, and the Dallas area started to be a big problem as well at this time. And so they brought everybody together to start talking about rose rosette. Now, if you don't know about rose rosette, it was first reported, it's a native North American disease, so you can't blame anyone else for it. It's us. And 1941, when it was first reported, the symptoms of rose rosette in California, Wyoming, and Manitoba, Canada, and in wild Rosa woodsii, which is native to the mountains of the U.S. and western U.S., and in some cultivated roses too. And as time went on, we found they were quite susceptible. The most typical symptom, of course, are rosettes. You can see that there. That's beautiful if you want to see a rosette. But if it's in your garden, you're probably not too happy about it. But here are some comparisons. This is some pictures from Oklahoma. They had wonderful rosette there in Tulsa. And so I took advantage of it and took some great pictures. And so you see on, well, I guess I'll have to do it with my hand because I don't have a pointer. But anyways, so this is the healthy one, and that's the rosetted one. This is a Duchère, I think. And this, again, healthy and diseased. And you can see the symptoms are different depending on the variety too, so it can be confusing. It's not only just a rosette. There's other things going on here, and the symptoms do differ with the variety. Here you see more shoot proliferation. You see the thickening of the shoot there coming. That's a diseased shoot there. Strap leaves, which are the thinner leaves that are very typical of rose rosette. Excessive thorniness, and you can see that over here, and they're pliable too. They're not real firm. They're pliable thorns. And the dark red shoots. Now you have to be careful with dark red shoots because there's some varieties that just have dark red shoots all the time, and that doesn't mean they have rosette. You sort of have to look at a combination of things. And even with the thorns, I mean, if you see a rugosa hybrid, it has lots of thorns, so it doesn't have rosette. But it's typically with lots of thorns. But you have to see the difference between the number of thorns compared to normal. So that's what you have to focus on. Okay, and of course there's fewer flowers, disordered flowers, and eventually the plant dies. That could take a year, could take 2 to 3 years, could take 4 years, could take more. And that's sort of the problem. If they died quickly, that'd be almost good. But the trouble is it can linger, and if it lingers, you have more inoculum there, and it's transmitted by a little mite that floats. And so it goes very nice throughout your garden. And the other thing, and we had this conference in 2013. In 2011 was the first time we identified what actually caused it. We were calling it rose rosette, but we really didn't know what it was caused by. But finally in 2011, we figured it out. And so that was a big milestone as well. And that gave us a lot of power to detect it. And again, transmitted, as I said, by a little mite, aerofoid mite, which is about 100 microns, and it just floats in the air. And you can see the pointer shows a little cigar, little squiggle there. That's the mite. And when it's slightly windy, it sort of stands up on its little hind legs and shakes its hands up, and off it goes. And it spreads very nicely. So it moves, again, air currents. But early on, we did not have diagnostics. So there was a lot of asymptomatic plants that were infected. Because once they get infected, it takes months to show symptoms. And these were passed around in commerce. And so it spread really quickly because we didn't know. Now that we know, it's not happening as much. And we're being a lot more careful, and we have the diagnostics to actually tell if it's infected or not. So we've come a long ways that way. Distribution, you can see, again, in 1953, and sort of in the West is where we saw it most, and then it slowly moved to the East. By the 90s, you saw it on the East Coast, and throughout the Midwest, and what have you. So it was really quite a buildup of the population. Of course, we had a lot of roses everywhere in the landscape, and they were all susceptible. The other thing that was susceptible was Rosa multiflora, which was sort of a weedy rose that was everywhere too. And so it was established in the multiflora as well. So it was throughout the Midwest and the East Coast. So this Rose Rosette conference was a career-changing event for me because, again, it brought the rose community together. They developed a plan and then told me that I was writing the project, which was fine with me, but it wasn't anything I was planning to do. And so we developed this specialty crop proposal, and lo and behold, we were actually funded, which surprised me. I was in Brazil when they tried to call me, because if you're funded, they call you. If you're not, they send you an email, But they finally, through the grapevine, I figured it out, and it took me a while to believe it, but it was actually funded. And this project, again, it was industry initiated. And that made, in this type of competition, that's extremely important. Without the industry support, you don't get funded. And so this was industry initiated. Industry was involved in development of the proposal as well as the objectives. And the final project involved 8 universities and the USDA. So it was a national project. And we did a whole range of things. And let me see, I think the next one shows it better. Well, let me go back up. I know I can do this. There. So if you look at the objectives, we have diagnostics. And that was important because we didn't have diagnostics yet. So the only way we could tell if it had disease or not by looking at it. And as I just told you, a lot of times they were infected, but they weren't symptomatic. Learned a little more about field management, breeding and genetics, which I was involved in, socioeconomics effects, and one thing they showed that by introducing disease-resistant, RRD-resistant varieties, it was a value of about $30 million a year to the industry. So it was a really valuable trait to put in there. And of course, a lot of extension, and we have an extensive a website with all sorts of information. And so what we're trying to do is understand this disease triangle, if you want to call it that. You have a rose rosette virus interacting with the rose, which interacts with the mite, and the mite interacts with the plant. So you have all these interactions that are affected by the environment. And so it's a really complex sort of thing. And so that's where we're focusing on, just trying to understand the basics. Because again, we knew very little about this disease yet. We knew what it caused, what caused it, and we had some preliminary data showing that the mite was, transmitting it, and maybe how to control that mite, but we weren't really sure. So we did a lot of work on just the basics. But my part was a question, is there resistance? Because there have been some reports of some resistance in some North American wild rose species, which I didn't really want to work with, because that means there's about 20 generations from there to a good variety. And so rather have something within the cultivated germplasm. So that's basically what we looked at. We set up trials. Now in Texas, in my plots here in College Station, we don't have rose rosette. And that's the way I want to keep it. So I send things to Tennessee and Oklahoma, or in this case Delaware, to see if I can kill them there. So we put 250 different rose varieties, a lot of them cultivated varieties, major varieties that all the various companies contributed to the project. And we spent 3 years. First, we tried to infect them. So we call that rose rosette augmentation, fancy word for putting infected shoots on the plants you want to infect. That's augmentation, okay? It takes a lot of time, but it was effective. We managed to kill a lot of our plants, infect a lot of them, and that's exactly what we wanted to do. And of course, we would infect them, and then for 3 years, we'd look at them and evaluate them for symptoms. But we also would we also look for virus as well. And we had virus titer indications of these things, which is the amount of virus. And so I'm not going to show you a lot of, a list of varieties here, but this little chart. And what this is, where the stars are, is where the ones that did not show symptoms after 3 years. Okay? And let me sort of explain this. If you look at the major varieties, mainly the China and the European blood, the hybrid teas, the grandifloras, things like that, those are mainly in this area. You can see those are all susceptible. You get over here, you get some background with Turiana, multiflora, and Cetidra in their background. You're trying to pick up some resistance there. And over here are some of the species, and they're all related species. They're all related to some of the North American species that we have here, and there's some Asian species that are closely related too. And so we're seeing these are from the part of the germplasm that hasn't been used much in breeding. So that's where we get in our rose rosette resistance, not where we normally breed. So we're going to have to bring things in. And so that's where what we learned that, okay, well, all the major varieties are susceptible. They eventually get it. Now there is a range of susceptibility, but they all will eventually get it, okay? But there's some we identified, at least after 3 years, didn't get it. Now I'm not going to guarantee they'll never get it, but after 3 years they didn't. That's a pretty good indication. That includes most of the rugosa hybrids, and Rosa rugosa and things like that. And Rosa carolina and Arkansana, those are Arkansana, Carolina, Virginiana, all those are North American species. Which makes sense from an evolutionary point of view. Usually when there's a disease, the plants evolve resistance to the disease. Okay? So that all makes sense. Okay, so we did this, and that project ended in 2019. But concurrently, I was also involved in this other rose breed project. Remember the rose breed 1? Well, there's a rose breed 2. And so there I focused more on black spot again, and worked with the University of Minnesota, which worked on black spot as well. So we started collaborating with the University of Minnesota on our rose research. And here it's combining disease resistance to horticultural quality in new rosaceae cultivars. Of course, it still included, blackberries and apple and peach and things like that, but I focused on the roses here. And so one thing we did was look at black spot resistance. Again, this is just to give you an idea of what it looked like. And again, let me explain this. This is a different set of varieties. So it's not the same one you just saw. So let me explain this a little more. Here you're seeing, this is Belinda's Dream here. Some of the interesting stuff out of the Cordis program. They got some resistance in there. But the bulk of the resistance is down here. You can see a lot of the shrubs. And then you get into things like Also Happy Candio. Now what's happening here is that you're getting parentage that has Ricciuriana and Satidra and things like that in its background. That's where the resistance is coming from. And so that's where we've been able to incorporate from a breeding point of view some of these genes from this. So these are mainly shrub roses. Let me see, there's also a few over there. But again, and over here, these are the Rugosa hybrids and things related to that. And it could not necessarily hybrids, but it could be Rugosa several generations back. And so we got things like that. Again, interesting. But we also look at Cercospora resistance. That's another problem that we have a lot of problems with. Now, it's generally not as devastating as black spot, but it's just as annoying. And so if you look at this, the resistance is from a different source. Here you see most of the resistance among the hybrid teas, the grandifloras, and more things like that. Here, right around the Rugosa materials, but again, not from the Ricciuriana-derived materials. Ricciurians tend to be susceptible to Cercospora, so you're getting it from a different source. So again, it's interesting to see, from a breeding point of view, where all these things come from. So, of course, the question was, are there disease resistance genes to these various diseases? And we had a whole set of genetic studies going on at the same time along with the variety trial. And so we were able to, after the end of this project, in 2019 to about 22, which is this year, last year, with supplemental funding, and now because our funding had run out, but we got supplemental funding from the university as well as the Basie Endowed Chair, from the American Rose Society Research Trust again. They were very, very helpful there. The Garden Rose Council and the GoFundMe program, which was coordinated by Pat Shanley and Paul Zimmerman, and had hundreds of donations to keep us going. And those were essential for finishing up this work. And so with rose rosette resistance, we found 3 important genes. And here I have LG5, 6, and 1. LG is just a chromosome number. It's called linkage group, but it's a chromosome number. So it just tells you which chromosome it's on, and we know the specific location and all that, which markers are linked to it. In black spot, there's 2 types of resistance to black spot. And this is important. There's a race-specific resistance. And you have to realize that black spot as a species is extremely variable. So just like in humans, we have different races and we're all different. Black spot, same way. They're all different. And they're going to have different virulence genes that will overcome different resistance genes. And so it's sort of a lock and key mechanism. Your resistance genes are your locks, and then the fungus comes with keys. If it has the right key, that plant is susceptible. If it doesn't, it's resistant. So it's race specific, okay? And then the other is partial or horizontal, which is resistance to all races. It's generally a little lower in level, but it works. And additive it's additive in the sense that the more doses, the higher the resistance. And so a lot of the breeding is to increase the doses. And cercospora, we found a couple of genes as well that induced good resistance to cercospora. But of course, they're all from different sources. Make things complicated. There's a few things with more than one, but not many. And so if you look at this one, this sort of puts it all together. And this is the second set, mainly cultivated things without the species. The dark stars on the outside is black spot resistance. The lighter ones, that'd be cercospora resistance. And the red ones, I think they're red, on the inside would be rosette resistance. So there's a few things that have more than one level of resistance or high resistance, but most of them are either one or the other. So it makes things a little more challenging because you have to put the resistance genes from different sources into one plant. So it's resistant to everything. And then, I mean, if that wasn't complicated enough, we have this chromosome problem. Because most of our roses are tetraploids, so they're a little more complex. So by an order of magnitude, actually. And so a lot of your diploids, you got 14 chromosomes there on the right. That's 2 sets of 7. But most of our garden ones are four sets of 7. So you have 28 chromosomes. And they're all moving around. They're not listening to me. They're doing their own thing, which is not good. And so anyways, the problem here was we didn't have the computational tools to analyze this complex stuff. Even though we could do all the DNA sequencing we wanted to, and we get millions of sequences, we couldn't associate that with the trait very easily because it was too complex. And so in 2007, I got this grand idea. I said, well, let me bring all these people together. All these people know how to program and are doing it. There's some work being done on potatoes, a little on chrysanthemums, and a little on this and kiwi, whatever. So I sort of connected with all these people and said, hey, why don't we get together and do a project together? And what I worried about is that they wouldn't get along with each other because they're all doing things a little differently. And of course, they always do things the right way, right? From their point of view. And I'm there, I don't care how you do it, as long as it works. You know, I'm a breeder, I don't care about the details, I don't want the results. And so, since we needed better analytical techniques, essentially software written for our analysis, I got them all together, we talked about it and put a project together. And we had a planning committee, so I brought them all together and found out they actually didn't kill each other, they actually talked to each other. And so that was a good step. And then in 2020, it was funded for a 4-year project. So we've gone 3 years, we have 1 more year to go. And we went to develop computational tools. And then I had breeders working with us. So of course, rose breeders, turfgrass, potatoes, sweet potatoes, kiwi, and blackberry, all polyploids, tetraploids and hexaploids. So some had 6 sets of chromosomes, even more complicated. And they said, yeah, we can work together. And so the software people would develop the software and the breeders would try to use it. And if it didn't work, we'd talk to the software people and say, hey, this doesn't work. And so we'd go back and forth, and it actually worked pretty well. I was surprised. And then, of course, we trained. We had a lot of training. And it was funny because in 2020, when it was funded, and the first thing I wanted to do was have a training workshop. Of course, what was happening in 2021? We had COVID. And so this was supposed to be an in-person project, right? So all of a sudden, I learned how to do Zoom. And so I Zoomed the project working thing, and I figured, okay, we have this large training workshop. We have people from all over the world Zooming in to talk and to participate. I figured, well, we might have 75 people because it's a pretty specialized area. Well, we had 350 people sign up. Now I had to go back to my administration and say, hey, my Zoom won't handle 350. You guys gotta give me a better account. So they did, and it actually worked pretty well. but now we're doing it in person, and I guess it works okay too. It's sort of nice to see real people instead of just faces. Anyway, so we did this, and we've really made a lot of progress. And so now we do have better computational tools that actually work, and we can do a lot more with our data. So it's extremely useful. We've identified the genes for black spot, rose rosette resistance. Some of the work done in the interim is because of this work. And we have better marker technology. Every year we get better and it gets cheaper. Because you can't spend your whole life savings on just marker technology, because then you can't do the breeding. And it is more reliable. So we're getting really, really good at this. And so the next step was to put it all together and go, hey, let's put a sustainable rose project together that includes rose rosette, includes black spot, and all this computational tool stuff. And so that's what I did. And that was a sustainable rose project, which was submitted several years. You can see in 2020, 2021, and finally funded in 2022. So it's always a process getting these proposals funded. It's generally not a one-year thing. It's a multi-year thing. Yes?
When you say funded, what kind of money are we talking about?
We're talking about $4 to $4.5 million. So $1 million a year to fund work.
Okay.
But there's 8 universities and USD involved, so it's parceled out to everybody.
Okay.
But it's a good slug of funding. But it takes a lot of work to get. Anyway, so here we have a lot of people involved, and it gives you an idea of who's involved in Tennessee, in Oklahoma, Ohio, Georgia, USDA, Minnesota. And again, the long-term goal here is to develop sustainable rose landscapes based on resistance to rose rosette disease and black spot. Now you can go beyond that. And we're always thinking of other traits as well, but those are the ones, when you write a proposal, you have to be focused. So that was our focus. And they bought it, which is good. You never know what they're going to buy until you're done. Anyway, so we have several objectives: develop sustainable rose cultivars, socioeconomic effects, as well as the extension component. I'm just going to talk about the top one. Otherwise, I might be here for a couple days because it takes a long time. But anyway, so we're going to focus on developing sustainable rose cultivars. Again, looking at rose rosette and black spot disease, and trying to identify additional sources of resistance, and then trying to verify and identify markers that we can use to follow the resistance genes in our breeding. So both those things are involved. Determine mechanisms, because we've determined that certain varieties don't get the disease, but we don't know why. And so that's a real important question if you want to deploy it in the field, to know why. And develop genomic approaches, again, marker-assisted selection. I continue with that because it's really a very useful tool. And to do all this and then put all those genes into one variety. So essentially, that process is called stacking. Okay? And so, new sources of resistance. We're now working in Oklahoma, Tennessee, and in Texas. Oklahoma and Tennessee, we're trying to kill them with rose rosette. In Texas, we try to kill them with black spot and cercospora. Or we evaluate them for that. That's what I meant. We don't kill them. So we both have cultivar trials and genetic studies. Right now we have, I think there's 5 or 6 different, there's maybe 8 populations and about 2,000 seedlings out there at all 3 locations. And a couple hundred varieties that we're going to put another 400 out next year. So about 800 varieties to look at to see if we can find new sources of resistance as well as understand the other sources. And so in our genetic trials, again, trying to understand things, we now know we have race-specific resistance. We have RDR1. RDR means rose diplocarpum rosea resistance, and diplocarpum rosea is just the name of the pathogen. So RDR is what they call it. 1 and 3 and 4, and they're from George Vancouver, and Bright Eyes is where those came from, RDR1 comes from a multiflora. And then looking for LG3, but we're looking at additional genes now. And we think there's additional RDR genes in Rambling Red and Baby Love and Hansa, so 3 additional ones that they're working on. And then horizontal, I think Miracle on the Hudson has additional horizontal genes, but we'll be looking for additional ones beyond that. But those are the ones in the genetic trials. For Rose Rosette, again, we know we have two important ones. There's another additional one, the LG6, so a total of 3. LG5 is the strongest and most important one. We find that both in diploid and tetraploid germplasm, which is interesting. But we're trying to develop more rapid ways of evaluating for Rose Rosette resistance, because right now it takes us 3 years in the field. I'd rather do it 6 months in a greenhouse. And so we're working with virologists to try to figure out how to do that. But again, looking for additional genes out of Morden Blush and Morden Fireglow. Now this is stuff with resistance from Rosa arkansana and Rosa rugosa background. So that's different from what we found thus far, which is more Richuriana background. Okay? So again, a different source of resistance, hopefully just as powerful. So how do you develop this sustainable rose? Well, again, trying to develop that rose with stable resistance to black spot and rose rosette resistance. That's the trick, and it's kind of hard to tell sometimes, but we'll do our best. We know the more QTLs or genes for resistance we have in a particular variety, the less disease we're going to get. Makes sense. We have data to show that. And so that's pretty straightforward. And so we want to stack all those genes. So in one variety, I want at least 2 genes for, if I could, 3 genes for black spot resistance and 3 for rose rosette resistance. So 6 genes, let's say. Let's try to put 6 genes in there. With a DNA test for each, we can do selection at the seedling stage. So we don't necessarily have to go out in the field to start crossing again. The genes available, there's just happen to be 6. How about that? Who would have known, right? So you have, for rose rosette, we have those 3 genes. Black spot, you have another 3 genes. Now, it sounds pretty simple. Just combine them, right? Piece of cake. Well, how long would it take? Let's look at a diagram here. Assuming they come from different sources, and actually most of them do. There's a couple that might be in the same source, but not many. And so if you start over there with 6 different sources, and they're all different plants with different sources of resistance, you cross them and you can put 2 of each together, right? And then you intercross all those, and then you can get them 3 with hopefully 4 genes in. Intercross all those, and eventually get to this. So at least 3 generations, right? Now that's with just 1 dose. And you might want more than 1 dose here. But let's say, okay, 3 generations, get 1 dose. Now you're somewhat looking at some of the phenotypic horticultural traits, but really you're focusing on these. And the key is, the more seedlings, the better. And so the more you can go through, the more likely you'll get some good flowers in there too, and not just really resistant plants. And so it takes a while, and thousands and thousands of seedlings. Remember I said 10,000 to maybe for 1 variety, maybe 2 varieties. So a lot of seedlings. And so with those number of genes available, a minimum of 3 cycles for 1 copy. Okay, not really looking at number of copies, but if you want more than 1 copy, well, you probably have to go at least 1 more generation. And if you want to look at other traits, maybe another couple more generations. Let's say it's only 4 generations. Let's make it easy. So if it's easy, you do it the normal way, and you make your crosses, 4-year cycle, 4 cycles, and then commercial evaluation, 19 years, 2 decades, that's all. Piece of cake.
For 1 rose.
For 1 rose, yeah. Well, you probably carry a bunch of roses, but yeah. I'll be 90 in 20 years, so I'd rather do it quicker. If you use marker-assisted breeding, you can do it in 11 years. Isn't that quick? You're supposed to say yes.
Yeah.
Oh, thank you. It's much faster. Of course, you know, you'd be carrying a lot of things going on at the same time. So, you know, it's cycle after cycle after cycle. It's just rotating and recycling things and trying to get the best things out there. And so, yeah, are sustainable rose landscapes possible? Yeah, I think they are, because we've identified the disease-resistant genes that we need initially, and we'll probably identify additional ones. We have marker systems developed, so we can develop the markers we need to follow those genes, and we're in the process of doing this. We have the computational tools because of the other project, and we have the genetic materials to begin stacking. And we've already begun this work, actually. And so it is possible. This will be a second generation of some of the stacking work we've been doing. And so, yeah, it's definitely possible, but it's going to take time. But not as much as you might think. Only a decade. Piece of cake.